So this past chapter was about models of the atom. And before I move on, I do want to talk a little bit about some notation and a possible error that I made. I didn't go back and look for it, but I might have made an error. Let's just think about a helium nucleus. A helium nucleus is actually an alpha particle. An alpha particle is a helium nucleus. And when Rutherford did his experiments where he discovered the nucleus in the gold foil, he was shooting alpha particles at the gold foil, not knowing that the alpha particle itself was a helium nucleus. He soon discovered, after discovering the nucleus, what the alpha particle was. But in any case, the alpha particle was simply known prior to Rutherford's discoveries as being a heavy particle that people could produce. I'm not entirely sure how they produced it. You could probably look that up. And that they used in scattering experiments if you needed a heavy particle, as opposed to, for example, the electron, which was understood to be a very light particle. There's a big difference in mass between a proton and an electron. The mass of the proton is approximately 1,836 times the mass of the electron, almost 2,000 times the mass of the electron. The mass of the neutron is about the mass of the proton. I think I just said the mass of the proton is about the mass of the neutron. They're actually different from each other in the fourth significant digit. So for all intents and purposes, the kinds of things that we're doing, we treat the mass of the proton and neutron the same. But it's good to know that they're slightly different. It has to do with the fact that they're both made up of three quarks, but because their charge is different, they're made up of three different quarks, and it's the slightly different energy of the different quarks that gives them the different masses. Okay, so let's get back to the alpha particle, or the helium nucleus. And the helium atom, you've got four in a neutral helium atom. You've got four electrons in some kind of orbit, whether it's quantized orbits of Bohr or whether it's electron cloud of Schrodinger. You've got four electrons in some kind of structure around the nucleus, and this is what makes up a helium atom, right? So that's a helium atom. The helium atom has two protons, and that's what defines, right? Z is equal to 2. That's what defines it as a helium atom. So the definition of an atom is the number of protons. The number of neutrons and electrons can vary, but what defines it is the number of protons. You typically think of an atom as having the same number of protons, neutrons, and electrons, your standard atoms. And that is perfectly fair to just think of your standard atoms as having the same number of protons, neutrons, and electrons. So it's neutral, therefore it's got the same number of electrons as protons, because the proton has the positive exact same charge as the negative of the electron. And typically most atoms, or a lot of standard atoms have the same number of protons and neutrons. But it is important to notice that an atom does not need to have the same number of protons and neutrons. And this is where I think I might have made a mistake. I think I mentioned that at the beginning of the lecture. I might have made a mistake in saying that the typical hydrogen atom has a proton and a neutron in the nucleus and an electron around it, and that would be your hydrogen atom. And that is not your typical hydrogen atom. Your typical hydrogen atom has no neutron. What Bohr really derived the structure of the atom for was the hydrogen atom, and then for higher atomic number, higher Z, for single electron atoms. But we really stick with the analysis of the hydrogen atom, and we didn't have to take into account really the mass anywhere until we talked about reduced mass. And we never really took into account reduced mass, so we didn't think about the fact that the typical hydrogen atom actually doesn't have a neutron. And that's something which I tend to forget. So I might have just naturally said, okay, every atom has the same number of protons, neutrons, and electrons, and I might have implied or even said that the hydrogen atom has a proton and a neutron. When I'm doing the reduced mass calculations, I'm all of a sudden realizing, oh, I forgot. Hydrogen atom, typical hydrogen atom doesn't have a neutron. And the reason you might wonder why most atoms have the same number of protons and neutrons, except the hydrogen atom doesn't. It has to do in part with the fact that two protons have a electromagnetic repulsion, and then they have the strong force attraction. And so it's that the neutrons help to mediate that electromagnetic repulsion. But in a hydrogen atom, since there's only one proton, there's no electromagnetic repulsion, and you don't need a neutron to mediate it. There is a common isotope of hydrogen, which has, and an isotope is, we'll define it in a second, but you might know isotope just means the different number of neutrons. There's a common isotope of hydrogen, and that's deuterium. So deuterium has a proton, a neutron, and an electron. So if I was talking about an atom with a proton, neutron, electron, I meant deuterium, not hydrogen. Deuterium is a naturally occurring isotope of hydrogen, by the way, and they occur in a ratio of about 1 to 6,000 in water. So in water, every 6,000th hydrogen atom is a deuterium atom, is a different isotope. So let's just describe what isotope means. First, when we're talking about the Z, the number of protons in the nucleus, that defines the number of protons in the nucleus. We did talk about Z as being the possible number of electrons as well. But when we talk about Z, we talk about defining the number of protons in the nucleus. And that's what defines the atom. And this is probably stuff you know, but I should be very clear about this. So often we don't worry about the Z number because if we're talking about a helium atom, we know that is by definition Z equals 2. If we're talking about a hydrogen atom, we know by definition that is Z equals 1. If we're talking about a lithium atom, we know if it's the third thing on the periodic table, so that is Z equals 3. And let's jump up. Let's go to uranium. I believe that uranium is by definition Z equals 92. So the name of the atom defines the number of protons. In other words, if you change the number of protons in the atom, you've changed the type of atom it is. So that's first of all. So often, we might not worry about the Z of the nucleus because we know it inherently by talking about the name of the atom. But the proper notation is to put Z in the lower left-hand corner of the atom's designation. So, for example, helium 2 indicates that helium has 2 protons. Hydrogen 1 indicates that hydrogen has 1 proton. Right? Lithium 3 indicates that lithium has three protons, etc. Uranium 92 indicates that uranium has 92 protons. So that's the correct notation for an atom in order to indicate the number of protons, and that number of protons, Z, is called the atomic number. Now, another more interesting or useful number, because the atomic number just defines the atom, so you don't really need to necessarily keep track of that. You can always look at the periodic table to figure out what the atomic number is. Obviously, you can look up any of these things, but more interesting number is the number of protons and neutrons. Now remember, a neutron has a mass approximately equal to the proton, so the mass of the atom is mostly defined by the protons and neutrons, since the electrons are such a small part of the mass of the atom. And so we have something which is called the mass number. And the mass number, which is A, is defined as mass number. Mass number is defined as the number of protons plus the number of neutrons. And this is where we got to be careful, and where I wasn't careful, is that the number of neutrons is not necessarily equal to the number of protons. It is not a bad assumption that for an average neutral atom, or an average neutral atom, it has the same number of protons, neutrons, and electrons, but it definitely is not always true. And it definitely isn't true for the hydrogen atom, and it generally isn't true for, or it seems like it. I haven't really done a study of it, but it's not true for the heavier atoms either. That they may really have a very varying number of neutrons. So the number of neutrons, if you change the number of neutrons in an atom, so let's take our helium atom again, ppnn, and that is the common isotope of helium, called helium-4. It's actually what I studied in graduate school. It's called helium-4. There's another naturally occurring isotope of helium, and it has it has only one neutron, and it's called helium-3. 3 and 4 are the mass number. Those are the mass numbers. It's the number of nucleons. These are called, the P's and N's, the protons and neutrons are called nucleons, the things that are in the nucleus. So it's the number of nucleons, the number of protons plus the number of neutrons. So the mass number just counts the number of protons and neutrons and will give you an approximate mass, because if you just take the mass number and multiply it by 1.67 times 10 to the minus 27, that gives you the mass of the nucleus, approximate mass of the nucleus. So the mass number goes up here, right, A. So your typical hydrogen atom, your common isotope, and we haven't defined isotopes properly yet, the common isotope of hydrogen doesn't have a neutron, so it's H11. Your lithium atom does have, or your helium atom has, your common isotope of helium, your normal helium atom, has 2 protons, 2 neutrons, so it's got 4 nucleons. Your lithium atom, 3 neutrons, 3 protons, so it's got 6 nucleons. Whereas your uranium atom, the most common isotope of uranium is actually, I believe, is 238. 238. So the uranium atom, the most common uranium atom, I can't say it properly, has 92 protons, but how many neutrons does it have? This has, didn't give myself space, 238 minus 92. Right, so the number of neutrons equals 238 minus 92. So the most common isotope of uranium has 146 neutrons and 92 protons, right? It's got a lot more neutrons than protons. So the the notation is for an element, whatever the element is called, let's say it's element X, the number of protons goes here, that's a Z. The mass number, protons plus neutrons, goes there. We often leave off the number of protons because X defines the number of protons, which is why you will more often see, when we're talking about the isotopes of helium, helium-3 and helium-4. Oh, I keep saying I get to define isotope. Isotope is the different elements that for a given atom, it comes in different forms with different number of neutrons. For a given atom, different number of neutrons. Those are the isotopes, where we change the number of neutrons, as opposed to ionizing the atom, where we change the number of electrons. The isotope, and we don't denote the number of electrons anywhere. Because the electrons are much easier to add or take away, I guess, in a sense. They don't really define the atom in a lot of ways. But the isotopes are where we take away neutrons or add neutrons. So helium-3 and helium-4 are the naturally occurring isotopes of helium. There is also a helium-2, it's just not naturally occurring. You can make a helium-2. In other words, you can knock both neutrons out of the nucleus. But that's not naturally occurring. So back to hydrogen, right? Hydrogen, there's a hydrogen 1 and a hydrogen 2. And hydrogen 1 is our common isotope of hydrogen. It's the one that we see that we see most often in water, whereas hydrogen with the 2, a mass number of 2, is deuterium, and that is with 1 proton and 1 neutron. And again, we're leaving off the atomic number. We're leaving off the atomic number, 2, because that is defined by the element itself, although you can put in the atomic number just to be clear. But so you do need to differentiate between whether the number is written at the top or the bottom when we're looking at this kind of notation. And the last thing I'll say is about isotopes is that there are naturally occurring isotopes, like the ones I have on the page here, hydrogen, deuterium, helium-3, helium-4, and there are unnaturally occurring isotopes, right, which we can create in the lab, and theoretically, I guess in theory, maybe you could create any isotope, right? You can put in or take away as many neutrons as possible. I guess in practice, that's probably not true, but that there are some There are some atoms that have only one naturally occurring isotope, I believe aluminum maybe, I don't know, and some that have many naturally occurring isotopes. So there's nothing particularly special about the number of isotopes, naturally occurring isotopes versus laboratory-made isotopes. So anyway, there you go. That's some notation stuff we really probably should have gotten out there earlier.